Hello and welcome to another lecture in this course on quantum computing based on the Qiskit textbook. In this lecture we are going to be moving from 1 qubit states and gates, as we saw in the last lecture, to 2 qubit states and gates, and in doing so we introduce a tool which allows us to generalize to any number of qubits, and that is the tensor product. So the tensor product is something that is used quite widely in linear algebra, so you may already know it. If you don't, let's take a look at a few examples. In this case, we're going to take some 2 by 2 matrices and do tensor products of them. So here, we're going to do the tensor product of this matrix A, which you already see on screen. And here is the symbol that depicts the tensor product. It is a circle with an X in. That is the most beautiful and accurate tensor product that I will draw in this entire course. And the tensor product gives us a 4 by 4 matrix. And I kind of think of it as inserting the matrix that's on the right here into the matrix on the left. So what I mean by that is we kind of make a bigger padded out version of the matrix on the left. So the top 4 elements are all going to be the top element of this matrix. So we take this element here and we copy it 4 times. And then we multiply each of those by a different element of the other matrix. So this one gets multiplied by B0, 0, this one by B0, 1, this one by B1, 0, and this one by B1, 1. So here we've kind of multiplied this element of the A matrix by this whole B matrix. And then we continue the same principle.
So here we're going to have A0, 1 and another.
So there's obviously a lot more elements to fill in this matrix, but I'm not going to do those ones because it's just using this same principle that I've already shown you, and I don't want to be saying A, B, 0 and 1 in various combinations for the next 15 minutes. So this is how you do a tensor product of 2 by 2 matrices, and I've also given you a flavour of the principle as to how you do it more generally as well. Now I've done it for matrices, let's do it for vectors as well. So let's take a vector, let's call it A, with amplitudes A0 for 0 and A1 for 1, which can be represented by this column vector A0, A1. And let's take another. I won't write it out fully in its Dirac form in this case, but it can be represented by a column vector B0, B1. So if we do a tensor product of these vectors, what we find is that again it's effectively like we're taking the first element of the first vector, A0, and multiplying it by the second vector. We're taking the second element of the first vector, multiplying it by the second vector, and that gives us a couple of A0s multiplied by the B0 and B1, and a couple of A1s multiplied by the B0 and B1 again. And if you're looking at the middle step here and thinking, what does that even mean? I'm just using it to sort of give a sense of the process. Don't take that notation too seriously. Okay, so this is the tensor product, and this is going to be pretty important for what we're going to say today. So let's just briefly review what happened in the single qubit case. We found that we can take a single measurement, and the Z measurement is our favorite, and there's 2 possible outcomes for that, 0 and 1. So we can define a state which we call 0, which is definitely going to give us the outcome 0 for a Z measurement. And we can define a state 1, which is definitely going to give us the outcome 1 for a Z measurement. And then any other state can be expressed as a linear superposition of those two states expressed as vectors. Okay, so what about the 2-qubit case? Well, in the 2-qubit case, if we were to have our Z measurement and we were to measure all of our qubits, then we would have 4 possible outcomes: 0, 0, 0, 1, 1, 0, and 1, 1. And similarly, we can define now 4 possible vectors that correspond to those 4 cases. We can define a vector that we're just going to call 0, 0, which is representing the state where we're definitely going to get the outcome 0 for both of our qubits. And there's also 0, 1, which means that we're definitely going to get the outcome 0 for this qubit, and we're definitely going to get the outcome 1 for the other qubit, and so on and so forth. Now with these 4 basis states, including also the 1, 0 and the 1, 1, we can write any state as a superposition of these. We can put some amplitudes in front of them, and again these amplitudes are going to be complex in general, and they are going to have to satisfy a normalization condition, and also global phase is again going to be irrelevant. So the probability of getting the outcome 0, 0 is again going to satisfy the Born rule, and it's going to be the square of the amplitude of this. And therefore, if we take a sum of all of these, so let's say sum over jk, where j and k are going to be the 2 indices that we're going to use, both of them can be either 0 or 1, then the sum of all of these jk's, or at least the magnitude squared, has to equal 1, because each of these individually are probabilities, so this is representing the sum over all of these different probabilities for these different orthogonal possible outcomes. So this is how you represent 2-qubit states. If you put 3-bit states in here, this represents the states of 3 qubits. If you put 5, it represents the state of 5. If you put 72-bit strings inside the kets here, it represents the state of 72 qubits. This is basically how you do it. But you might be wondering, well, what does this state look like? Well, what is the state 0, 0? How can it be represented as a vector? And similarly for the other basis states. Well, we can represent these vectors as tensor products of the vectors that we already know. So in this case, we will get 1, 0, 0, 0 as a 4-element vector, so a vector in a 4-dimensional space that represents this state. For 0, 1, we have the tensor product of the 0 state, which is 1, 0, with the 1 state, which is 0, 1. So the first 2 elements of this 4-dimensional vector are basically going to be a copy of the second vector, 0, 1. But the next 2 elements are basically all multiplied by this 0 here, and so there will be 0 as well. So 0, 0, and so that is what you get. And you can think of this as each of these correspond to a different possible bit string. That one's 0, 0, that one's 0, 1, as we've seen. This one's going to be 1, 0, and this one is 1, 1. Also, if we have 2 single qubit state vectors, such as some state vector we'll call A, with amplitudes A0 and A1, as we already had in our example earlier. And then we have another state vector B, with some amplitudes B0 and B1. Then when we take the tensor product of that, it's going to be a description of a 2-qubit state, which basically just describes the state in which one of the qubit is in the state A, and the other qubit is in the state B. So you can still do all of your familiar single qubit stuff on 2-qubit states, but you just have to use the tensor product to make them more general. So let's just write down that the 2-qubit state is A tensor B to have that on the board. If we were just talking about single qubit states and you wanted to apply an X operation, for example, to the qubit in state A, then you would just apply the X operation to that vector. And you might remember that this can be expressed by this particular matrix. Well, when we're thinking of 2 qubit states, you can't just apply this 2 by 2 matrix to this 4-dimensional vector that describes the 2 qubits. You have to find a 4 by 4 matrix which is going to have the effect of doing an X to the qubit you want to do an X to and doing nothing to the other qubit. Well, we already know how to do nothing. That's represented by the identity matrix, which is this particular matrix here. And with these we can do a tensor product again. So we can do the tensor product of X and the identity, and this gives us a matrix which applies an X only to the qubit we want to apply an X to and does nothing to the other one. So if we look at these, well, we see that the first 4 elements of this tensor producted matrix are going to be 0, and so are the ones on the other part of the block diagonal, and then it's going to be identities basically on the off diagonal blocks. So let's just put that in. We're going to have 0, 0, 0, 0, 0, 1, 1, 0. This is what you signed up for, isn't it? Listening to a guy talking in binary. And there you go. This is a matrix which only acts non-trivially on a single qubit, but it is phrased as a 2-qubit matrix, so you can apply it to 2-qubit states. And similarly, if you had 3 qubits and you wanted to do an X on the middle one only, then that could be described by a matrix which would be identity, tensor, X, tensor, identity. And just another note, another way that people often write the identity matrix is with a blackboard bold 1, like this. If I ever in this course use that accidentally instead of an I, then now you know what it means, because it's quite easy to slip between the two because these are 2 very well used conventions. Now we've taken a look at some of the single qubit stuff from last time and phrased it in this 2-qubit context using the tensor product. We can look at some truly 2-qubit operations. So we can look at something which cannot be expressed as the tensor product of 2 single qubit gates, and that is the controlled NOT. So the controlled NOT has non-zero stuff only on these 2 blocks in the diagonal, and you can see that this block effectively looks like the identity and this block effectively looks like an X. Everything else is 0, so just for clarity, let's draw those zeros in. Often people can't be bothered to draw all of the zeros in matrices like this because they're zeros, but it's good to do that the first time. Now to think about how this works, one thing we can notice is that this block effectively acts on the states spanned by 0, 0 and 0, 1. So these elements of this matrix come into effect whenever we have a 0 for this qubit. For the other block, it is relevant to states spanned by the other 2 states, 1, 0 and 1, 1. So it's relevant for the states where we have a 1. So what this matrix is effectively telling us is that when we have a 0, this is going to do nothing because we have an identity here. And when we have a 1, then it's going to have the same effect as an X and swap around the amplitudes we have for these 2 states. And so this is how you can read off from this matrix that it represents a controlled NOT, where the control is the qubit that is on the right of these bit strings and the target is the qubit that is on the left of these bit strings. If you want the matrix that is the other way round, then that's going to look like a different matrix, and you can see that in the textbook, or you can calculate it yourself. Now let's apply the controlled knot to a particular state so we can see an interesting example of a 2-qubit state which cannot be represented as the tensor product of 2 single qubit states. We'll start with a state which can be represented as the tensor product of 2 single qubit states. We're going to have a plus state for that qubit and a 0 for the other qubit. Now the plus state, of course, can be represented as the superposition of 0 and 1, and that is what we are tensor producting with this 0. Now I'm sure you have many years of experience looking at how the operations of addition and multiplication play together, and it's exactly the same when you have the addition of vectors and tensor products of vectors. So we can just write this as 1 over the square root of 2 multiplied by 0 tensor 0 plus 1 tensor 0, which is more conveniently written as 1 over the square root of 2 times 0, 0 plus 1, 0. When we apply the controlled knot to that particular state, what we are going to find is that it just applies the same relationship that we've looked at before in the atoms of computation and in Hello Quantum, where we can just have this interpretation where we think, well, if this control qubit's in the 0 state, nothing's going to happen. If the control qubit's in the 1 state, then it's going to flip the target qubit, which is this one here. So it's going to flip that 0 into a 1. So let's write down the state after the controlled knot has been applied to it. We get the 1 over root 2, of course, still. And we write down what happens to the first term after the controlled knot's applied to it. Well, because the control is in state 0, nothing happens, so it's exactly the same as before. And then for the other one, because the control is in state 1, the other qubit state gets flipped from 0 to 1. So we get the state 0, 0 plus 1, 1. And there is no tensor product of 2 single qubit states that you can find which will yield this result. This is a truly 2-qubit state. And whenever we have a truly multi-qubit state which cannot be represented as the tensor product of single qubit states, that is called an entangled state. And so having an entangled state just means that we can't describe things as just lots of single qubit things, but it's become truly multipartite. And that's why entangled states are key for quantum computing, because if you could just describe everything as lots of single qubit states, you could just simulate everything as lots of single qubit states, which is very easy to simulate, and you would never find anything that could do anything that a normal computer cannot. You need truly multipartite effects, multi-qubit effects, to find an advantage of quantum computing over conventional computing, and that is why you need entanglement. So now we're going to look at doing the controlled knot to this state, which is the tensor product of a plus and a minus, and that gives us 1 over 2 because the two factors of 1 over root 2 multiplied together, and we're going to get superposition of all of the basis states, but we're going to have a few phases of -1 in there because of the phase that comes from the minus state. And that phase of -1 comes in whenever we have a 1 on the on this particular bit value, and that's just because of the phase coming from this side. Now we're going to look at cases where we have controlled knots which are controlled on this qubit and targeted on this qubit, and that is the opposite of the examples that you will see in the textbook. And the reason why we're taking the opposite of the textbook is because controlled knots do go both way round, so it is important to see them both way round. It's not like I'm choosing an opposite convention where only one convention should exist, Both conventions exist simultaneously. They are just how you choose the control and the target of your control knot, and that's why I'm choosing it the other way around, to give you some experience of it the other way around. Also, I prefer it this way around. Okay, let's apply our control knot to this particular state. And basically, when we're applying a controlled knot to this state, which we can call plus minus, then we can just go through all of the basis states and see how the controlled knot gets applied to each of them. In this first case, we are controlled on 0, so nothing happens, and this basis state goes through unchanged. The same is true for this second basis state, but for the other two, the control state is 1, and so the target is going to get flipped. So this 1 means that the 0 gets flipped to a 1, and this 1 means that the 1 gets flipped to a 0. And this is the state we're left with at the end. Now we see we get the minus phase here and here, and that is exactly what you would find if you were to take the tensor product of the minus state with the minus state. I'll leave you to verify that for yourselves, but it is quite an interesting relation that we found here. If we take the plus state on one particular qubit and the minus state on the other, then we apply a Cx to that, then we end up with a minus state on both the qubits. So the qubit that we're thinking of as the target is actually unchanged in this process. The qubit that we are thinking of as the control does get changed. So there is something interesting happening here. To see what this interesting thing is, we can note that the state that we have considered, which is plus tensor producted with minus, can be expressed as a superposition of 0 on the control qubit, tensor producted with minus, and 1 on the control qubit, tensor producted with minus. So we can look at these two states individually, and we find that 0 tensor producted with minus when we apply a Cx to it. If we follow the same steps as before, we will find that this can be expressed as, well, as 0 tensor producted with minus. And this shouldn't be too much of a surprise because, of course, the control qubit's in the state 0, so nothing should happen. But if we were to apply it to the other state, so the control knot applied to a 1 tensor producted with minus, what are we going to get? Well, in this case, the control qubit is in state 1, so we should be applying an x to the minus state. And when you apply an x to a minus state, it does not affect that state, but it does give you a global phase of minus. So what we get out here is a global phase of minus, but otherwise the same state. However, when we apply to this superposition here, the global phase of minus is not a global phase anymore. It changes this phase from a plus to a minus, and that is how it changes this plus into a minus. The global phase becomes a relative phase and therefore becomes relevant. And this is the effect that we are getting here, and this effect is known as phase kickback. And it is quite a useful effect that we see in many algorithms. If we were to look at a few more states, what we would find is that the Cx has the effect of turning the plus plus state into the plus plus state, so no change there. There's only plus 1 phases, so there's no phases to kick back. The plus minus state, which is the one we've just looked at, has the effect of turning them both to minus. The minus plus state comes out as the minus plus state. There's also no effect there because the phase on the target, which is where the phase is getting kicked back from, is just plus, so it just multiplies things by +1. And in the case of minus, we also get a phase to kick back, and it flips that initial phase, so we get plus minus. And with this truth table, you can come up with a completely different interpretation of what the controlled knot does. Instead of looking on the control qubit, seeing if it's 0 or 1, and using that to decide whether it does an X to the target qubit, it also effectively looks at the target qubit to see whether that's in the state plus or minus. And in those cases where it's in the state minus, it applies a Z to the control qubit because the Z operation is the one that flips pluses to minuses and vice versa. So don't get too stuck on this idea of the controlled knot being this thing that looks at the control and uses that to decide whether to do an X on the target. That's one interpretation, but there are multiple interpretations to what a controlled knot does. It is a truly quantum gate and therefore has lots of lovely mysteries for us to ponder upon. To complete our meditation upon the controlled knot, let's look at it in a Dirac notation form. But first, let's just remind ourselves what it looks like in matrix form. So this version of the controlled knot, which has the control on the left and the target on the right, can be written in a block diagonal form, where the first block is the identity and the second block is an X. And remember that this first block pertains to any state for which the control is in the state 0, and the second block pertains to any state for which the control is in the state 1. And this means, and there's a bit of a leap between these two steps. I'm not saying that you should instantly be able to say, I see where this is going. But hopefully once it's gone there, you'll be able to say, I kind of get how it got there. So this means that we can write this down as a projector onto 0. So this is something that just means that this term is only going to affect things where the control qubit is in state 0. And then we tensor product that with the identity. There you go. I've done it already. Slipped in a blackboard bold there just to confuse you. Well, maybe to confuse myself. And then we tensor product that with an X when we have the term which has 1s on the control. So this is another way of thinking of the controlled knot. Now we can use the expansions of these gates into their Dirac notation form as outer products. So the identity is one that can be expressed as the outer product of 0 with itself, with the outer product of 1 with itself. But we can equally express it as the outer product of plus with itself, plus the outer product of minus with itself. And X can be represented as the gate which turns 0 into 1 and vice versa, but it can also be represented as the gate which turns plus into itself and gives minus a phase of minus. So now let's see what the first term here comes out like when we substitute in the identity that we've just written down. And so we can write this as the outer product of 0 with itself, tensor producted with the outer product of plus with itself, plus the outer product of 0 with itself again, because we're still on this first term, tensor producted with the outer product of minus with itself. And then we repeat the same things, but for the other term. Now we repeat the same things for the other term. Let's just make those appear by the magic of editing. The differences in these two new terms are that we have the outer product of 1 with itself here, because this represents this term, and also that we have this phase of -1 here, which comes from the fact that we are representing an x rather than an identity. Now we have this, we have the ability to collect terms again. Now let's collect together these first two terms, which both have the outer product of plus with itself on what we are thinking of as the control qubit. So this means that over on what we're thinking of as the control qubit, we have the outer product of plus with itself, and this is going to be tensor producted with whatever we get when we collect these other two parts together, which are the outer product of 0, the outer product of 1, both added. This gives us, of course, the identity. So this first pair of terms becomes the tensor product of identity with the outer product of plus with itself. And now we collect together the other two terms, the ones that end in the outer product of minus with itself. And there we get the outer product of 0 with itself and the outer product of 1 with itself. But this time, rather than being added, there is a minus between them. And this completes this picture where we can either see the controlled knot in the normal way, which is represented by this first line that we wrote down earlier, or we can represent it in a way where it's looking to see whether the target qubit is plus, and if so it does nothing, or is minus, if so it does. So there, I've told you a lot about controlled knots. We've really sort of meditated on controlled knots and looked at some of the maths of controlled knots for a while, because controlled knots are really very key, and there's a lot of cool stuff to just thinking about controlled knots. Thinking about Grover's algorithm, Shor's algorithm, all that nonsense. Controlled knots. That is more than enough coolness to keep you going for some time. But anyway, we're going to have to move on from just thinking about controlled knots, unfortunately. So now we're going to look at a few circuit identities, which are a few simple ways of combining gates to get useful effects that are used quite a lot in quantum computing. Now we've already looked at the idea that if you have a particular representation of a state as a ket, then there is an equivalent representation of that state as a bra. Now similarly, if you have a particular representation of a gate as a matrix, let's just say U to be general at the moment, there is an equivalent representation U dagger, which is known as its Hermitian conjugate. And basically, the only way we're going to really be talking about this at the moment is whatever effect U has on a ket, U dagger has the same effect on a bra. And there's a notion of a Hermitian matrix, which is one that is equal to its own Hermitian conjugate. Now most of the gates that we've looked at so far are Hermitian. So the X, the Y, the Z, the Hadamard, the controlled knot, these are all Hermitian gates. So the Hadamard has the effect of turning 0 into plus and plus into 0. Now it also has that same effect on bras. So here we're seeing it having this effect on kets. But if we were to express it in bra form, we would also find that we get the same thing. And also for the H being applied to the plus state and giving us a 0. And I won't write them down, but H applied to minus gives us 1, and H applied to 1 gives us minus. Now this means that we can use H to transform different Paulis to each other. The X gate, for example, has this form where it turns 0 into 1 and 1 into 0. Now if we were to apply a Hadamard to both sides, so H, X, H, then you can hopefully see that the H applied to this 0 is going to turn it into a plus. The H applied to that 1 is going to turn it into a minus. The H applied to that 1 is going to turn it into a minus. the h applied to that 0 is going to turn it into a plus. And so what we're going to get is plus minus from that first term and minus plus from the second term. So we get a gate which turns plus into minus and minus into plus. And that is exactly what the Z gate does. So by taking a X gate and doing a Hadamard before and the Hadamard after, then the effect we get is that of a Z gate, which is something that should be familiar to you if you've gone through those exercises of Hello Qiskit. And also, if we did an H before and after a Z, we would get an X. And this gives us a way of turning controlled knots into controlled X gates and also controlled X's into controlled knots. Because the controlled knot, as we just saw, can be expressed in this form where we have these outer products for 0 in the first term and for 1 in the second term. And then on the control we have the actual effect of the gate, which is an identity for the first term and an X for the second term. Now if we were to apply the gate identity tensor H before the controlled knot and identity tensor H after the controlled knot, then the identities would not do very much to those parts of this equation before the tensor product. In fact, they would do nothing at all. But after, we would get H identity H, and we would get for the other term H X H. So what is H identity H? H times identity is just H, so H identity H is just H squared, and if you multiply that to itself, you'll find that this just comes out as the identity. So this first term is going to be still the identity, whereas the second term gets transformed to having a Z here for exactly the reasons we saw just now. So we have got, instead of having a controlled X, a controlled Z. Another useful circuit identity concerns rotations. So we are going to compare what happens when we do a Z rotation, so a rotation around the Z axis by some angle, and exactly the same thing, but with an X before and after. So how do these two things compare? Well, as an example, let's take a particular point on the block sphere, and we're going to make it easy for ourselves by picking one that we know, which is the plus state, because it has a property which is going to be quite nice for us in a moment. And let's just apply a rotation around the z-axis. So let's apply some rotation around the z-axis that brings us, say, to this point here. So now let's look at a case of doing an x and then that same rotation and then another x. So what happens if we do an x in this case? Well, because we are looking at an example which starts off in the plus state, and we know that an x applied to the plus state is just the plus state, then we do this x and we go nowhere. Then we do the z rotation, and because we start off in the same place and do the same rotation, we get to the same place. And then we do another x, and this x, well, what is an x? But it's a pi rotation around the x-axis, and so this is now going to take us over here. So the final point after the x rotation x process is to bring us not to the point where we ended up after the simple rotation, but instead to bring us to this other point over on the other side. What we find in this case, if we actually do some more examples or even just multiply the matrices together, is that the rotation we get is again around the z-axis and again by the angle theta, but now in the other direction. So effectively moved in the other direction by preceding and following the rotation with X gates. So this is a way of flipping our rotations using X gates. With that in mind, here's a circuit for you to think about with 2 rotations and 2 controlled knots. If you had no controlled knots, what you would have on the bottom line is a rotation around the z-axis by some angle theta, followed by a rotation around the z-axis by the opposite angle. And so these 2 things would combine to be the identity. Nothing would happen. You would rotate and then you would unrotate. You would get back exactly to where you were. However, if we were to insert some x's in here, so if we were to put some x's around this negative rotation, then it would flip it, as we've just seen, into a positive rotation due to the effect of these flipping these signs of rotations. And so what we would have is a combined rotation of 2 theta. And so whether or not we get a rotation of no angle at all or of 2 theta depends on whether or not we are inserting x's here. And that's exactly what the controlled knot does. Whether or not we effectively have x's on this bottom line is controlled on what the top line is doing. And so whether or not we have a 0 state for the top qubit or a 1 state for the top qubit, the bottom qubit is either going to experience no rotation at all or a z rotation by this particular angle. And by choosing theta, you can make this angle whatever you want. And so what we have here is a controlled rotation around the z-axis. And this trick works exactly the same way for y rotations as well, because similarly, if we have an x and then a y rotation by some angle theta, and then another x, this is the same effect as having a y rotation by the negative angle. And so that gives us the exact form of this controlled rotation that we see in the textbook version of this lecture. Now, if you look in the textbook section, you will find more examples of circuit identities. And also, if you go through the entirety of Hello Qiskit, you go through multiple circuit identities there as well. So there are things like making a swap gate or how to construct a Toffoli out of single and 2 qubit gates. I won't go through them all explicitly now, but you now have the tools to start trying to understand how these things work for yourself, and there is no better exercise in knowing how quantum computing works than to do just that.